Here's a list of all your parent functions and equations, and they aren't in the same order, in case you were curious about that. And I'm asking you 3 questions on the first page about these parent functions. The first question is, are any of these pairs of functions inverses of each other? Secondly, give you some information about what are called invertible functions and ask which of these functions are not invertible. And thirdly, I ask you to look and see if any functions are inverses of themselves. Are they that is any function its own inverse? And how would you figure that out? If you think you would like to give this a try yourself, go right ahead and you can check you can start the video or check the answer key online and check your answers. But if this doesn't make a lot of sense to you, you can do it along with me. Let's start out with the first question. Which pairs of functions are inverses of each other? So hopefully you'll remember that we talked about log base 2 of x and 2 to the x. The exponential and logarithmic functions are inverses of each other. You can see their graphs. They look like mirror images across the line y equals x. And then maybe you'd think, well, x cubed and the cube root of x seem to be inverses of each other because they would certainly be opposite operations. Also x squared and the square root of x. Those are really the only 3, but there is a problem with x squared and the square root of x. You can see that if I were to take the inverse of the x squared function, it would look like a sideways parabola, which isn't what the square root of x looks like. The square root of x just looks like the top part of that. It turns out that the inverse of x squared is not a function. Likewise, the inverse of the absolute value of x would not be a function also. These 2 functions and another one up there, which is 1 over x squared, are functions that are said to be not invertible. So let's take a look at what it means to be invertible. A function is said to be 1-to-1 if every x pairs with exactly 1 y and every y pairs with exactly 1 x. If you look at the x squared function, every x pairs with exactly 1 y, which makes it a function. But every y does not pair with exactly 1 x. And as a matter of fact, every y seems to pair with 2 different x's, if we look at it that way. So when we switch x and y, notice then we have in the inverse every x pairing with more than 1 y, which makes it not an inverse, makes it not a function. So back to the definition. A 1-to-1 function is said to be strictly increasing or strictly decreasing, which means that the graph may curve, but it never changes direction. Well, notice this graph definitely changes direction. If you look at some of the other graphs, like x cubed, it curves, but it's still increasing across the whole length of the graph. This one's always decreasing. This one's always increasing. Notice this graph here is increasing then decreasing, so it's not strictly increasing or strictly decreasing. This graph A, the 1 over x graph, is kind of an odd one. It's decreasing, and then this section is still decreasing. It never increases as you move from left to right, so it would still be considered strictly decreasing. So it is a 1-to-1 function. Okay, so back again to our definition. If a function is 1-to-1, there's supposed to be the word it in there, it is said to be invertible because its inverse is also a function. A function is 1-to-1 or invertible if it passes both the horizontal line test and the vertical line test. In other words, you heard if I can draw a vertical line anywhere on the graph and it only crosses the graph once, it is a function. If I can draw a horizontal line across the graph any place on the graph and it only touches one point, then its inverse is also a function. Here, its inverse is not a function because it does not pass the horizontal line test. So which functions are not 1-to-1? Well, we already talked about x squared and the square root of x, or the absolute value of x, and the 1 over x squared function. None of those are invertible. They are not 1-to-1. It turns out anytime you have an even function, it won't be invertible because it won't pass the horizontal line test. Odd functions always will be invertible. If it's neither even nor odd, sometimes it's invertible, sometimes it's not. You just have to check. What can we do then with a function that's not invertible? Well, we can limit its domain. If we only look at the right-hand side of the function, the part where x is greater than or equal to 0, then its inverse is the square root of x. If we only look at the left-hand part of the function, the part where x is less than or equal to 0, then its inverse is negative square root of x. So if we limit the domain, we can find an inverse function. The third question on page 1 is, are any functions their own inverse? Now looking at their graphs, you would have to say it's a function that is symmetric with the line y equals x. And it has to be, if you switch x and y in the equation, you'd get back to what you started from. Well, it turns out there are two functions that fit both of those criteria. The two functions that are inverses, that are their own inverses, are the lines y equals x. Kind of obvious, it has to be symmetric to itself. And if you switch the variables in the equation y equals x, it's the same equation, obviously. The other one is y equals 1 over x, f of x equals 1 over x. If you switch x and y and solve it, you get back to the same equation. Also, you'll notice that if you draw the line y equals x onto the graph, it's symmetric with itself. It already has that symmetry. There are other graphs besides that, but those are the two parent functions that we have that are their own inverses.